Very good afternoon to everyone. So first of all, I welcome you all to join our RISC-V booth here. I'm Niraj, Dengale from Andis Technology. I'm working as a senior engineer in Taiwan headquarters, and I would be talking to you today about if RISC-V is ready and it can become a force in the HPC domain. Okay, so for the RISC-V SoCs market trend, you can see this the pie chart here. You can see from the 2021 to 2030 in various applications, RISC-V is growing. What we will focus on in this talk is basically application processors and also about the AI accelerators. So mostly focusing about the high performance computing applications here. We see a rapid growth in the RISC-V domain on these specific applications, and I will talk about what we have in-house to cater to these growing needs for high-performance computing. So Andis provides a wide variety of RISC-V cores, starting from small basic microcontroller CPUs and going up to vector cores and application processors and into data centers. So depending on how much operations per second you require for processing power you require for your application, like in smart cameras you would need around 100 megaops for smart home applications, like around 1 gigaops, and it can go up to almost 100,000 tops for the HPC applications. So for HPC applications, I will talk to you about some RISC-V cores that we have in the market, which are specifically designed to cater to those audiences which want these high performance from the RISC-V CPU cores. The first core I would like to highlight is the AX65. So this is our latest offering, and also it is our most powerful CPU core to date. It's a 64-bit CPU core, which is following the RISC-V extensions, RV64, GC, bit manipulation, and as well as some crypto extension, and the CMO for the cache management operations. It is fully RVA22 profile compliant, and it's a 13-stage pipeline architecture. You can configure it up to 8-core multiprocessors in this core. You can have different configurations. The most is 8-core. They have 4 wide front-end decode, so quad issue, and it also has 128 entry reorder buffer. The branch target buffer is also 2-level, and the TAGE-L branch predictor allows you to have more accurate branch prediction. There is also 64 kilobyte of private instruction and data cache, and 8 megabytes and 16-way shared cache. So the bus interface is 256-bit XE4, MMIO, and IO coherence port. Coming to our vector core, this is a AX45 MPV. So this core has both scalar as well as vector units. For the scalar part, it is following the RV64 GC-BP RISC-V extensions plus Andis extensions. So there are some Andis optimizations and extra additional extensions that we provide, which are supported in all of our core offerings. There are up to 8 cores per cluster that you can configure, and because this is an X45 MPV, all our cores which are starting with the A abbreviation, they are application processors, so they are all Linux running compatible. The MMU configurable, MMU it supports SV39 and SV48, which are RISC-V standard for the physical memory to virtual memory translation schemes, and also the DSP for digital signal processing SIMD instructions. It also has the 2-level translation leukocyte buffer, also physical memory protection, so you can configure what kind of memory regions you want to be cacheable, non-cacheable, to limit the access to those specific memory regions. Branch prediction is also 128 entry branch target buffer. And I would like to highlight one Andes extension, which is ACE. We call it is an Andes custom extension. So this is something that we provide on top of standard RISC-V extension. Andes custom extension enables you to add your own instruction. So you will design your own hardware instruction, and we have a tool called Copilot. So what it is going to do is it will bring the instruction that has been created by the user, and it will combine it with the existing RTL of the CPU core. So you will get a new core. In addition to the existing instruction set, you will have this one extra instruction, so that you can minimize the cycles or for a specific memory, for a specific algorithm that you want to design as a hardware instruction. You can compare, you run some profiling or performance monitor to see how much is the difference you are getting after and before you created this or your own custom instruction. For the memory subsystem, I will talk about the high bandwidth vector local memory later. So it supports the HVM. It supports instruction and data local memory. These are the tightly coupled memories, and also configurable from 0 kilobytes to 8 megabytes. And for instruction and data caches, it is configurable from 8 kilobytes up to 64 kilobytes. You can also have an optional level 2 cache, for which size can be either you can have 0 kilobyte, no L2 cache, or if you want to have it, it can go up from 128 kilobytes up to 8 megabytes. And it also includes the multi-core cache coherence logic, so the cache coherence is taken care of. So for the interface, it is for vector. For interrupt, we implement the RISC-V standard, which is the vector platform level interrupt controller with 1023 inputs and 255 sources. So for the interface, it also has debug and trace interface, and bus interfaces are basically AXI master and AXI slave port. So through this AXI slave port, you can also access the local memory. Optional I/O coherence port lets you have coherence with the masters outside the core, and there are some power saving features that Andes brings, which are called power break. Also have dynamic frequency scaling and wait for interrupt. So you can let the CPU go into sleep mode and send an interrupt to wake up and resume the instruction execution. For the core mark performance of X45 MPV is 6.04 per megahertz, dry stone is 3.39 per megahertz, and spaking is 4.07. So the performance you can see is compared to ARM A53, A55 level. Coming to the vector unit of X45 MPV, it follows the RISC-V standard extension for vector. It also has some Andes extensions. On top of that, we support data types like int4 and vector.product. We also support the ZVA combinations, and there are total 32 vector registers in the vector processing unit. You can have different LML configurations to couple these, group these vector registers together depending on what kind of LML length you are using. There are 12 different vector functional units, so depending on what kind of vector instruction is it an ALU instruction, is it division or other types of vector instruction, it is going to send to that specific vector functional unit, and that unit will start executing that instruction. Because the 45 MPV is a dual issue CPU core, 2 instructions can be issued in parallel. And the full vector loads support, we have the unistride, strided load store, unit stride fault only first. So all the different kind of load store instructions are supported. ACE-RVV is Andes custom extension for vector. What I talked about earlier was for scalar. So ACE-RVV is letting you access the VPU directly, the vector registers. So you can also write the hardware custom instructions for vector instructions as well. And the anti-streaming port, it is giving you another path to access the VPU through AC load store instructions. So you can use your memory connected to the vector processing unit through this anti-streaming port to bring in the data directly to the vector processing unit, so you don't stall the main scalar pipeline when you are doing the load store for the vector registers. The data formats which are supported are int8 to int64 and floating point 16 to 64. In addition, Andes supports bfloat 16 and vector small int handling, int4 load, and vector dot product. ASRVV I mentioned earlier, and the VLAN here for the 45 MPV, it can be configurable from 128 bits to 1024 bits. Similarly for SIMD DLAN, it is configurable. These are all the possible combinations of VLAN and SIMD DLAN for X45 MPV. I mentioned it briefly earlier, the high volatile vector local memory, which is high bandwidth HBM. For HBM, it is a low latency access, enables you to have a low latency access from VPU to HBM, and back-to-back HBM access is pipeline. So HBM is reachable by the scalar unit, but for VPU and external coprocessor or DMA, you can access it via a subordinate port, this SUBP. VPU will access the HBM using the DLAN wide interface, and maximum DLAN is of course 1024 bytes. And VPU can do the DLAN bit access per cycle on each bank concurrently. So these are the HBM banks. You can add, depending on your requirement, you can add HBM banks. And you can select the address bit which is configurable. So if you want to enable this HBM, all you need to do in the RTL is basically let the CPU in the configuration tool know that this memory region exists, and this memory region is specific for the HBM, which is the high bandwidth vector local memory. This is the pre-integrated AXI platform, So in addition to this beach part, which is the 45 series core, in the sky blue color part, we offer everything you see in this picture is offered by Andes. We call it A350 subsystem. So in addition to the core itself, we provide the bus matrix, the APV bridge, and all the peripheral drivers that you see here. So and also the DMA controller. What it is doing is basically giving you almost kind of like a small SoC with drivers and everything, so that reducing the time for evaluation and also reducing your time to market. Of course, you can add your own IPs or third-party IPs to this XI bus matrix. You can directly connect. It supports various masters and as well as slaves. This is something new from our side. It's a Chilai development platform that we have. Chilai is a very beautiful mountain in Taiwan, and it is for the main goal of Chilai development platform is to enable the software development for application processors. It is running on 7 nanometer and running 2 of our cores, which is X45MP and NX27V. So NX27V is the vector core, and 45MP is the application core which can run Linux. The Linux distribution it is running is OpenSUSE, and the applications which are already capable, it is capable of running are LibreOffice, YouTube, TinyYOLO, and more. So it is already ready, this platform. You can go ahead and play with it. So this is something that we have ready for software development. Okay, coming to the software part, we also have for ANDLA what we have this deep learning accelerator, as well as the neural network software development kit. talking more about the ANDLA i350 accelerator. It's a Andes deep learning accelerator, which is for high performance and efficient deep learning, and it is scalable and multi-GLA. So the good thing about this accelerator, it is compatible with all the CPU series that Andes is offering. So you take any 22 series, so from 22 series up to the highest 65 series, all the Andes cores can utilize this Andes ANDLA. So the main target applications is the NN applications, which are for image and video, as well as speech or voice and audio processing. The performance with configurable max, you have 32 to 4096, and int8 is the data type which is supported, and the performance which is targeting is 64 gigaops to 8 teraops. It also has onboard memory, which is configurable from 16 kilobytes up to 4 megabytes. And also the power efficiency is around 5 teraops per watt. It's at 28 nanometer. Okay, so for the working flow of ANDLA, the first stage is to load the offline compiled commands with command streams, the weights, the input feature maps in the system memory. The system memory, it could be flash, SRAM, or DRAM. The second stage is the setup. So the CPU will set up the ANDLA with all the addresses like SRAM, DRAM addresses. It will give it to the CPU, and it will let it know all the memory regions that will trigger the ANDLA. The third stage, the ANDLA will automatically start running and run the iterative runs to load the data into local memory and do the computing and store the results to the system memory. And the fourth stage is after the computation is done, it will send an interrupt to the CPU when it is finished running all the commands, and it will just basically let the CPU know that I have finished the processing and your computed data is ready. For the software part, we also provide an NN library which has around 120 functions in 8 different categories, basically for the neural network functions like activation, basic math, concatenation, convolution, and fully connected. So these are all the different categories that we have our functions for the NN specific library. You can utilize this ANDLA, the NN library, into data center applications for high performance computing. You can either have a control in the control cluster. You can have CPU core like X45MP, which is the application processor, and in the compute clusters like Meta have done in their application, can have multiple NX27Vs. So to summarize, I would say RVV, the RISC-V vector standard, has opened the doors for a lot of high performance computing, and this is also delivering new CPU cores which are compliant with the latest RISC-V standard. And the RISC-V vector application processors and Linux processors can really help to run high performance computing applications. And you can also have flexible design because you can add your own instructions through ACE, the Andes custom extension, or ACE RVV, where you are writing your own instruction for the vector specific instruction. So all in all, I would say RISC-V is ready for HPC. I hope it will be a very good next few years for the HPC applications as far as RISC-V is concerned. Yeah, thanks a lot for listening to my talk, and if you have any questions, I would be more than happy to take them.